Hi everyone, welcome to this Cloud Native Geospatial webinar for the Pacific region. So this webinar is co-organized by Radiant Earth and Development Seed, who are a part of this Cloud Native Geospatial Foundation, and we're excited to introduce you to different Cloud Native Geospatial file formats today, and also some of the use, how some organizations are using it in their work. So I'll first hand it off to Michelle, who will give us a bit of quick housekeeping, and then we'll get on with the session. Michelle, over to you.
Thank you, Wei Ji. Hello, welcome everyone to our second International Cloud Native Geospatial webinar series, Introduction and Use Cases. So what to expect today? We're hoping that through this webinar, you take away two main things: an understanding of what options exist for cloud optimized data, and then also to learn about how other organizations and teams are implementing cloud native geospatial, and today specifically in the Pacific region. Some housekeeping things to keep in mind today: this webinar is being recorded. We will send out a link to this later once we have edited and cut down and have it all ready for you. It will also be available on YouTube, and we'll share that out on our socials. And we have a Q&A section of this webinar. So if you look on your screen, you should see an area that's just a simple chat that you've probably seen in other Zoom calls, and then a specific spot for questions and answers. And so if you're just saying hi and introducing yourself, you can put that in the chat. But if you want to ask a question for any of the panelists today, please put it in the question and answers area. Wei Ji will be monitoring this, and we'll make sure that all your questions get answered. And if they're not answered, we can always export that and make sure that your question gets answered at some point later on. But there will be time for questions after each speaker. Each speaker will speak somewhere between 15 and 20 minutes, and then have a 5-minute slot for questions specifically about their talk. And then at the end, we'll have an additional block for about 15 to 20 minutes for general questions and discussion. And so there's plenty of opportunities to ask your questions. So please send those in the chat to make sure that we see them. And yeah, as I said, time for question and answers after each speaker. So as I mentioned, this is a part of a greater series. Last week, we had our first one, which was the Brazil perspectives. It seemed to go really well. It was all in Portuguese, so I didn't really catch most of what was happening, but it was really great to have something more specific to a country and have use cases in that specific area. Today, either the 14th or the 15th, depending on where you are, we have the Pacific perspectives happening today. And then next year, we plan to have African perspectives sometime in March, and hopefully others to come. We're really enjoying having focused webinars on different parts of the world to broaden our understanding of how cloud native geospatial is being used internationally. I'm a developer advocate at Radiant Earth. A little bit about Radiant Earth: we are an incubator for data-driven initiatives, services, and 21st century institutions needed to foster and share an understanding of our world. So how we are accomplishing this goal of ours is through two main initiatives. The first being the Cloud Native Geospatial Foundation, which is what has helped put this webinar on today. The aim of the Cloud Native Geospatial Foundation is to increase adoption of highly efficient approaches to working with geospatial data in the cloud and the internet. And then on the other side of Radiant Earth, we have Source Cooperative, which is a data publishing utility for easy data sharing over the web. So if you're curious about Source Cooperative, you want to learn more, you can go to radiant.earth and learn more about Source Cooperative and more about Cloud Native Geospatial Foundation there as well. And we are partnering with Development Seed to put these webinars on. Development Seed's mission is to ensure that every decision that could possibly be positively be affected on Earth is made with the best data available, Earth data. The team is a global international team of engineers, developers, designers, and data scientists. And Development Seed builds impactful tools by leveraging open data, cloud computing, artificial intelligence, machine learning, and product development to empower decision makers. So we're really happy to be working with Development Seed to put all this on. And with the team that Development Seed has, we've gotten some great brains that are here today, and then also that were here at the Brazil webinar that just make this all possible. So with that, I'm going to stop sharing my screen and hand it over to Wei Ji to give the introduction to cloud optimized data formats.
Awesome. Thank you, Michelle, for all the housekeeping stuff. I'll share my screen now. Slideshow. Okay, so yeah, welcome to this webinar. So my name is Wei Ji. I'm a Geospatial Data Scientist at Development Seed. Was one of the co-organizers for this webinar. And so I'll first give you an introduction to cloud optimized file formats. The survey we put out, I think over half of you do know a little bit about cloud optimized formats, but if you're not too familiar or you're a bit new to the space, don't worry, we'll have you covered. First, we'd like to start off with what does cloud optimized mean? Cloud optimized means we're kind of flipping the paradigm of data as something that is stored to something that is used. So file formats that are cloud optimized means they're designed to be read by users more often than they are written. So the way I like to think of this is imagine that you're watching this recording on YouTube. You don't really want to download like a 2-hour video before you watch parts of it. So nowadays you can stream data like minute by minute. So this is kind of the concept cloud optimized is going for. So you can do partial reads. You just read the parts that you want. You can read the data in parallel. So computers nowadays, they have lots of cores, or you might have graphics processors. And that allows for really parallelized compute. So cloud optimized formats are optimized for that. Usually cloud optimized data has this concept of it has this block of metadata that's stored at either the start or the end of the file. So that metadata contains a pointer to parts within that file. For example, if you want to look at a video at 1 hour, the metadata can point you to where to look for. So that helps with the partial reads or the portion. So that's kind of like the core parts of what cloud optimized means. They're like designed to be read efficiently. And a good cloud optimized design might also include other features. For example, usually nowadays we access data through the internet. So rather than through like disk drives, sending floppy disk or floppy disk. So we want to optimize sending data over the internet, usually through the HTTP protocol. And some cloud optimized formats, they support some what's called range requests. So you can select parts of the file, again, like taking subsets of the file rather than reading the whole file at once. Cloud optimized formats typically also supports lazy access. So instead of loading an entire file, which could be several gigabytes in size, you can have enough metadata to know what's in the file and kind of only access or run your computations on the file once you've know what you're working with. So there's like a lazy element of not loading everything into memory first. And also you can do like intelligent subsetting for the spatial world. That usually means something like spatial subsetting. So just reading the parts, locations of the file that you need, for example, over a city or a town rather than like a whole country. And also for reading these cloud optimized formats, there's a whole ecosystem of like software libraries that can allow you to leverage the full power of these cloud optimized formats. And we'll hopefully go into some of that later today. So that was about what cloud optimized formats were. Well, why do you want to cloud optimize your data? So there's kind of two sides to this. There's on the data provider side and also the user side. But the key takeaway is that it means like less downloads. So less downloads for the provider means reduced server costs. So it's less strain on compute servers. And for the users, they spend less time. We can spend less time downloading data, or if we only need parts of the data, we don't need to download the full data. We can just download the subsets that we want. So, and there's also this concept of data approximate computing nowadays. So where instead of bringing your data to your computer to do the processing, nowadays you can shift your compute to where the data is located, usually in like a cloud or high performance computing environments. So cloud optimized data kind of enables that. And before, there were also a lot of like client server architectures where you have to set up like a dedicated server, hire like a server admin to make sure the servers are running 24/7. But nowadays, with cloud optimized formats, it allows for like serverless architectures where you can like dynamically query data straight from a file stored on an object storage, rather than like having a server running 24/7 to do that. So things like dynamic tiling are enabled by cloud optimized formats. Cool. So that's why some of the reasons why you might want to cloud optimize your data. What does cloud optimized data look like? So to use data, one of the first things people want to do is to like visualize what the data looks like, right? So here we're showing an example of a cloud optimized GeoTIFF or a COG, where COGs have this things called overview levels in them. So if you're looking at the raster map at a very high zoom level, zoomed out view of say like an entire continent, you don't want to be reading like millions of pixels at once. You just sometimes what you just care about is resampled view of it. So COGs have this concept of overviews where you can look at resampled versions at different zoom levels. And then as you zoom in, you can look at just the areas you want. So on the right, if you zoom in, you'll get to like lower overview levels, and then you can just grab the tiles you need. So you're never reading like the entire file at once. You're only reading what you care about too. And this allows for like faster visualizations of raster data. That's just an example, but of like raster data. But geospatial data is more than just raster, right? There's also like points, lines, and polygons. So all the data we collect using like remote sensing or Earth observation, depending on how you collect it, it could be like from a satellite altimeter, a satellite synthetic aperture radar. All of those, we're talking sometimes about lots of different file form data structures. And you might want to store things differently than just a raster. So that brings up the case that actually cloud optimize isn't like just one thing. There's like many different ways of doing things. And in the next few minutes, we'll kind of walk you through some of that, how you can use different types of cloud optimized file formats. And again, this is a bit challenging. Cloud optimizing is a bit of a complicated topic because there's actually no one size fits all for data. So the table on the right here shows 6 columns representing 6 different file formats. And for the rows, there's different types of data, such as imagery, swath, trajectory, point clouds, etc. So depending on the type of data you want to store, you might certain file formats might be more suitable or less suitable. For example, if you're you want to store point clouds, you might want to store it as a parquet. type rather than like a geotiff, which has is not really ideal for storing point clouds. So we'll get into some of that here. But basically, if you're for the two main types of geospatial data people usually work with, they're like rasters or vectors. For rasters, cogs are the typical format. If you have like highly dimensional data, Zarr or Kerchunk might fit your bill a bit more. If you're working with vector data, Flat GeoBuff and GeoParquet are good choices. And also, if you're working with like LiDAR point clouds, tile-optimized point cloud or CUPC and entwined point tiles are what you should be looking at. And all of these different formats, they have a traditional equivalent. So cogs are a replacement for geotiffs, and Zarr's replacement for NetCDF, for example. And also for the vector world, the bottom two rows, LiDAR last files can be replaced with like CUPC, EPT, shapefiles, GeoPackage, GeoJSON. They can be replaced with Flat GeoBuff or GeoParquet. So note that these formats, while they might seem quite new, they're actually not too new. They've been around for quite a few years now. A lot of these have standards in place. So they're like OGC standards. Either they've been formalized already or they're currently in development. And so there are good ways to interoperate between all of these file formats. Converting, for example, between GeoJSON to GeoParquet is possible through some of these standards in a platform agnostic way. Cool. Now I'll walk you through some of these file formats I mentioned. So I mentioned cogs before. So cogs are a good representation for multi-band raster data. So if you have an X and Y coordinates and multiple bands, for example, RGB bands, red, green, and blue bands for optical imagery, cogs are ideal as a storage format for this. What makes a cog and not a geotiff is it has this concept of like overview levels, which I mentioned early on. So instead of reading like the millions of pixels at the highest resolution, if you're at a more zoomed out level, you can read just the subsets you want, like a resampled part. And as you zoom in, you would be reading maybe like the higher resolution ones. But again, not the entire file, just like the squares or the tiles that you are interested in. So that's a cog. And this is how it's kind of structured internally. So it has a big chunk of, at the start of the file is the metadata. And this metadata points to where each tile, a tile being like a square region on a map. And each tile contains like the overviews and also like the raw data. So there's different overviews representing, which are resampled versions of the raw data. Cogs support something called HTTP GET range requests. And that just means you can efficiently like query the tiles you need within a cog file rather than all of the data. So that's for a simple raster use case. If you're working with more complicated data sets, such as climate or ocean models, you might have like lots of data variables such as like temperature, pressure, precipitation, etc. Zarr is one of those file formats which allows for complicated n-dimensional arrays. The way it works is you have these things called chunks. Chunks are, you can think of them as like 3D cubes, which store a data variable in dimensions. And each of these chunks can be compressed so that they remain small in file size. And the metadata associated with Zarr is not within the Zarr itself. Zarr like data itself, it's kind of like external to the data files themselves. So people can point to just the metadata and then from that metadata, they can jump to the actual data files. If you're interested, you can look up more about what Zarr is. Sometimes we might not have like the benefit of creating our own data from scratch. There are also archival file formats such as netcdf or HDF5. And if you have archival formats and you don't want to necessarily reprocess all of them into a new cloud optimized file format, Kerchung's a way to go to do that. So Kerchung is really just a way of creating like that metadata that points to parts of the data file where so it's like an index where you can point to the different parts of the data file. For example, if you want to query data from, let's say you have time series data, you want to query from the year 2010 to 2020, Kerchung can sort of build that index for you and then read just the parts of the netcdf or HDF5 file that you want. So it's like a lightweight way of cloud optimizing your data without necessarily creating that reprocessing your data from scratch. So we've talked about raster file formats. If you're working with LiDAR point clouds, you might be familiar with like LAS or LAS files. COPC is like the cloud optimized version of that. A COPC is a valid LAS file, so any tools you have that can read a LAS file can also read a COPC file. And a COPC has octrees instead. So octrees are kind of like the overviews in a cloud optimized GeoTIFF. And I won't go into too much detail here, but check out COPC if you're interested in LiDAR data. There's also another cloud optimized format called endpoint point clouds, which I won't cover today, but those are sort of the two options you have for cloud optimized point clouds. Next, we'll cover vector file formats. So there'll be two I'll cover, GeoParquet and FlatGeoBuff. GeoParquet is this columnar data format. So instead of storing your data as rows internally, a GeoParquet file will store the data as columns. So if you have a column such as date time, all of those date times will be stored together inside the file structure. And the benefit of this is data with the same type is really easy to compress. So you can get really small file sizes with a GeoParquet file. And they're really good for analytics, where you want to compute, say, the statistics for one column. GeoParquet can be a single file or a multi-file. And what you gain with compression is you can like split, the data into multiple files. So you don't have to store all of the rows in one file. You can split it into different row groups. The downside to GeoParquet now is that it doesn't have a spatial indexing yet. So it's in the works. And hopefully someone will implement that in the coming months or years. So that's GeoParquet. Another file format is a flat GeoBuff. This is a single file. And the flat GeoBuff has metadata at the start. It does have a spatial index, which is a Hilbert sorted R3 index. This index is optional, but what this index allows you to do is it would point you to where spatial features within the data. So you can really like just access the data you want from this like big chunk of data. The limitations of flat GeoBuff, it's typically bigger than storing a GeoParquet because you can't compress it. And this is because compression doesn't allow for random reads in this case. So yeah, so that's kind of the trade-offs between like GeoParquet and flat GeoBuff. One is compressed, no spatial index, whereas this one has spatial indexing, but it's not so compressed. Cool. I know I went through this super fast, but we have this Cloud Native Geospatial Guide at this website. So check this out if you want more technical details on some of the file formats I've covered just now. And I'll just leave you with also this slide on additional resources. And yeah, shall we take some questions? Take a look at I'll stop sharing now. look at the Q&A. Is 3D tiles? Let's answer some of the questions. So Pacific Spatial Solutions, is 3D tiles cloud native? 3D tiles. What do you mean by 3D? I know there are like different types of 3D tile file formats. Some might be cloud native, some might not be. So it depends on which 3D tiles. You mean, do we have Pacific? Oh yeah. Can we unmute?
Hi, can I ask a question? So yeah, it's my question. Can you hear me?
Yes, I can hear you.
Yeah, okay. So the OGC has a 3D tiles specification, right? So now is a version 1.1 is released already. And then we often use 3D tiles for visualization using a Cesium.js. And then the 3D, those like a 3D like buildings and the point cloud is kind of the divided up to the small cubes, for the efficient visualization. It's not like data analysis or anything. It's just for the visualization. It's really efficient file format. And I always wonder, the Chris Holmes talking about the GeoParquet and other stuff, but I feel like the 3D tiles also really cloud native for the visualization part. And then I don't know, is that qualified? I don't know, is that part of the cloud native stuff or not? That's my question.
Yeah, cloud native, it's more a concept. It's not like what I showed before are just examples of cloud native file formats. There are like definitely like other ones out there. From what you described with the 3D tiles, it does sound like it does have this concept of you're able to access just parts of the data you want.
Okay.
That does get easy to read.
Okay. Yeah.
But and it's cloud optimized. It's also like a spectrum. So there's the minimal you can do, for example, overviews. That's probably some of those basics. And then there's also fancier stuff you can do, streaming from like a object storage, which might be a bit harder to implement, but that doesn't necessarily say it doesn't mean it's not a cloud optimized file format.
Okay, great, thank you.
Cool. Shall we take some other questions? What is the I'll answer this from Robert Cheatham. What is the difference between CUPC and Entwine? So Entwine is sort of like an earlier file format. It's stored as like JSON. So the metadata for Entwine is stored in JSON files, and that would point to like the last files. Whereas for CUPC, it's the metadata sits within the file itself as like the header of the file. So depending, and there's benefits for both. Like CUPC, if you want to append data, you kind of have to rewrite the index. Whereas for Entwine, you can keep the files, like the LiDAR last files as is. But if you want to add more data, you kind of just update the JSON index. So hopefully that kind of answers your question. Yeah. And other questions? That's helpful. Thanks. Okay. And Humate Imran, hope I'm pronouncing this correct. What kind of format is ideal for data that has both raster and vector elements? Yeah, this is something I've been thinking of recently as well. It's tricky. Like Zarr maybe has a bit of that, where Zarr is not actually just for raster data. Technically, you could store like vector data in like a Zarr as well, as just like a one-dimensional array. So that's one way to go. And also Parquet, nowadays Parquet has this concept super new, which is called like a fixed shape tensor array. So you can store like a column within a GeoParquet, but within that column, each cell would be kind of like an image or like a raster. But it's not like a traditional raster in that sense. So there's kind of two ways to do that. You can either have a raster that stores vector data or have a vector table format that stores raster data. So it's I think it's something that would be interesting to explore for the community in the coming days. Cool. And one last question before we move on. Marcus asks, good morning, everyone. You're interested in streaming large point datasets, and you're thinking about flat GeoBuff, but interested in the potential for dynamically creating tiles for quick visualization. Can anyone on the panel expand on this? Cool. Streaming large point datasets. So I'm thinking you mean almost like point clouds, or at least just X and Y points. Yes, flat GeoBuff is potentially one way to do this. It depends on how large your region is. I'm not sure if it's sufficient to, like, say you have multiple flat GeoBuff files and you want to stream it. There might be ways to do that. One of my colleagues at Development Seed has developed this tool called Longboard, which is this arrow-based, geo-arrow-based way to like stream lots of data at once. So I'll post a link later in the chat and you can check it out. But I think we can move on maybe to the next speaker. Alex, do you want to start sharing your screen? Oh yeah, thanks, great.
Yep. Hey, everybody. Can you see my screen now? Right. All right. Well, welcome, everybody. My name's Alex Leith, and I'm here to talk about a brief history of Digital Earth. So I'm going to introduce myself. I'll go really quickly through some of my background. I want to go through the history of Digital Earth platforms, and then frame that all up into cloud-native geospatial. So I think this follows on quite well from what Wei Ji was talking about. So I won't get into those details, but I'll talk about some of the use cases around cloud-native geospatial. So I did university a long time ago and used random forest to forecast urban housing growth, but I called it the development of a spatial model, and I didn't call it machine learning. And so I haven't got a job at OpenAI building the future of artificial intelligence. Instead, I've ended up in Earth observation. I worked with some reasonably big data for a long time, built some public web mapping systems, did some work on global metocean data for a startup, built some shiny 3D web applications, worked on a big data use case with Digital Earth Africa and Digital Earth Australia, working with petabytes of data. Had a brief stint in IMOS where we work with long time series sensor data. So so lots of sort of different unstructured data. And now I'm working on Digital Earth Pacific and some other projects, really interrogating and supporting people to work with large volumes of cloud-native data formats. For a long time, really, my focus has been working with data and often about getting data and visualizations, making them more easily accessible. And I really think that cloud native helps us do that in a massive scale, in a way that's hugely empowering. Hopefully I can expand on that throughout this talk. Firstly, I've got a bit of history here. So in 1998, Al Gore gave a speech around Digital Earth. And there's a big paper there, and you should go and have a read. It's pretty great. It's it's visionary and it's good, and we haven't quite achieved it. But there's a couple of things which I've pulled out of there. One, we have an unparalleled opportunity to turn a flood of raw data into understandable information about our society and our planet. In the first stage, we should focus on integrating the data from multiple sources that we already have. And in the long run, we should seek to put the full range of data about our planet and our history at our fingertips. And I think we're getting up to that point. So navigating a history of Digital Earths, and I've worked on 3 of them: Australia, Digital Earth Africa, and Digital Earth Pacific. Digital Earth Australia was started around about 2010. There's always going to be more projects and more history, but around about 2010. Australia, back into the history, Australia was a downlink for Landsat. So Landsat, the older Landsat satellites didn't have a lot of storage on them. So the images that they captured, they had to stream into downlink stations. And that got stored on tapes. Sometimes those made their way back to the USGS. There was a project in Australia called Unlocking the Landsat Archive, which involved getting those tapes that were off in a vault, putting them onto spinning discs, sending a copy to the USGS, but then building software tools to help work with that data to sort of lift it up into the hands of the scientists so they could derive information products from it. That bit of software was called the Australian Geoscience Data Cube. It was rewritten later to be more flexible with projections and other things, and called the AGDC version 2, and later was renamed to be the Open Data Cube, which is much more friendly name. And Digital Earth Australia support government and industry in Australia by making Earth observation data more easily accessible. One of the key things that Digital Earth Australia does is they develop their own analysis-ready data, or level 2 processing of Landsat. And this is an example which I think is really clear about the opportunity or the necessity really for level 2 data. So optical Earth observation data goes through a range of processing levels. There's level 0 data, which is raw, level 1 data, which is called top of atmosphere, which is essentially what you can see from space. But then you go through another process where you remove atmospheric influences or changes or absorption of spectra, and you end up having surface reflectance. So level 2 analysis ready data is surface reflectance data. And here on the left, we have an image of level 1 data, and the index is the modified normalized difference wetness index, which should be from -1 to +1, where -1 is probably not water and +1 probably is water. And here it's highlighting that the clouds are probably water and the lakes are less likely to be water. And on the right, we've got the level 2 data, which has removed some of that systematic error, and it's really highlighting that the water is water, which is what we want. My point here is that analysis ready data is really important. So Digital Earth Australia processed Landsat and Sentinel-2 data up to level 2 surface reflectance, and then they produce some low-level derived products like a water observations from space, which is for every pixel over all of Australia, over all of the history of Landsat, whether or not we think it's water. They run a fractional cover, which is the percentage of a pixel that is likely to be vegetation, brown vegetation or not vegetation, and other things like geomedian, a cloud-free, robust, statistical mosaic, annual mosaic with variations or variance and deviations. And then like higher level products like coastlines, water bodies, and this image on the right here, which is the land cover classification. An example of what data versus information looks like. This is a single scene of Landsat, and this is a water observations from space scene, and it's during a flood in New South Wales. And if I flick between them, you can see that there's information buried in there. But when we turn that into analysis, we've got a little 8-bit version of the world where the blue is the water, the white is the cloud, the brown is the hills. And if we flick between a couple of different scenes, you can start seeing that you can count all the blue squares and you've got some kind of actual information coming out of this. So to wrap that all up, Digital Earth Australia produces, stores, processes, and shares open access analysis-ready data, and they produce derived data products. Now, Digital Earth Africa was started in around 2020. It's funded by US-based philanthropic called the Helmsley Charitable Trust, as well as the Australian Department of Foreign Affairs, Australian government. And their goal is also to make data more easily accessible, to develop capacity across Africa. And there's a broad range of applications: mining, land cover, surface water, agriculture, coastal erosion and accretion. And Digital Earth Africa's architecture, I drew a picture of it once and I love showing it around because it really shows the kind of platform architecture where you have a baseline of data, analysis-ready data, as we talked about before, and then derived and summary products. And then you've got a set of services sitting on top of that. So that's web mapping services, analysis hubs like Jupyter Hub, metadata explorers, and so on. And Digital Earth Africa and Digital Earth Australia are structured in a way now where they store all of their data on the cloud, on Amazon Web Services and S3 as cloud-optimized GeoTIFFs with common metadata using spatiotemporal asset catalog metadata and an API, which means you can use the tools that they use, that we use, like the Open Data Cube, or you can go through a web map and explore the data visually. But also you can go direct to the data and the data APIs and use that without having to use the opinionated way. So we have a suite of opinionated services, but we also have unopinionated direct data access. And this is one of those big opportunities of the cloud native paradigm, is that you can use this data in your own way. There's not a specific bespoke API. You don't have to access the spinning disks in the supercomputer, which is how Digital Earth Australia used to have its access. You can do it how you want. So we do some reasonably big data processing, or we used to when I was at Digital Earth Africa. So this example was pretty fun. There's about 6,000 CPUs and over 30 terabytes of RAM being used to take about 400 terabytes of Sentinel-2 data over a whole year, and to summarize that into a single geometric median with absolute deviations. There's a lot of fun being able to do this kind of stuff. And then Wei Ji said you get that parallelization from the cloud optimized GeoTIFFs. This is kind of what it means. You can have like hundreds or thousands of processes streaming data out of an object store, and it's built for that horizontal scalability. So you actually get the performance of a file system just through the huge parallelized data access. This is the kind of result that we get. And really what I want to emphasize here is that Digital Earth Africa, they don't produce analysis ready data. They take a copy of existing analysis ready data from the USGS, from ESA. They copy it to Africa, to an Amazon, to a cloud data center in Cape Town. And then they process and share that analysis ready data and derive data products and make that all available and accessible for free. But to emphasize, Digital Earth Australia gets the low-level data and creates analysis-ready data. Digital Earth Africa just get analysis-ready data. And that brings us over to Digital Earth Pacific, where we actually don't need to take a copy of the data anymore. We use a copy of the data that's already on the cloud, and we can just get productive doing the analysis, using cloud compute, using all the same paradigms as before. But the really complicated work of producing analysis-ready data, and it's even quite complicated to manage the synchronization of petabytes of data. That work has already been done, and we can just stand on the shoulders of big cloud providers and really empower the people of the Pacific to get stuff done. So here are our goals within Digital Earth Pacific, and I'm not going to go into the detail there. It's pretty early days. We had a launch just a couple of months ago, which is really exciting. We've got a couple of fantastic products, and I encourage you to go and visit the website and have a look at that. But in really simple terms, Digital Earth Pacific only does the processing and the analysis and the sharing of open access derived data products, because the baseline analysis ready data is already there and already organized, and that's really empowering, as I said. So that brings us to kind of like a bit of an aspirational thesis on my part. So the present future of Digital Earth platforms is that global analysis ready data is now accessible with low to zero barriers, which is amazing. When I started working with the Open Data Cube 5 years ago, this was not a thing. And now it's kind of ubiquitous. It's there as cloud optimized data. So there's petabytes of Landsat data going all the way back to the 1980s. Sentinel-2, 2 satellites capturing data every day from 2016 through till yesterday, and you can get that easily. Sentinel-1's a little less easy to access and less broadly accessible, and one of the satellites is broken, but that's still a fantastic data product. And there's new commercial satellites practically every week. You know, Planet is building new satellites that capture data that's reasonably interoperable with Landsat, which means that you can potentially integrate those big reference products going way back to the 80s with high resolution data that's captured every day. So cloud native geospatial, the core concept is shifting from downloading data before you use it to streaming it straight into your analysis. You're removing any middleware APIs and so on. You're disintermediating the data. It allows the data custodians to organize the data once and for people to use it directly. The spatiotemporal asset catalog API-based catalogs make that stuff interoperable. And I'll talk about that in a minute. But like Wei Ji said, again, it's just data accessible over the internet using standard HTTP. And that's really cool. So one little use case before I finish up, I'm sure I'm running out of time, Wei Ji, is a project I'm working on now called the Vietnam coastlines. We're producing coastlines data over Vietnam, and we're doing our analysis all the way back to starting with 1985. And we have a contour there from 1988. And this is streaming USGS data, but it's also uses an elevation model, which we stream out of Microsoft's Planetary Computer. And it also uses an ESA world cover product, a land cover product, also from the Planetary Computer. And the point there is that we're using a stack API from USGS to discover 40 years of Landsat data and load that into memory. And we're combining that with the stack API from Microsoft's Planetary Computer and discovering data from them and loading that into memory. And we're working with these together to build, to realize global interoperable cloud native data processing at a pretty significant scale. And it's really cool. So as a conclusion here, Al Gore's Digital Earth vision was for an interoperable global platform. And that inspired vision can now be realized using cloud native geospatial. And I suggest that the future is here, but it's not evenly distributed. And some of my work or my goals is really to help distribute that more evenly. So thank you for listening.
Awesome. Thanks, Alex, for your talk. It's really wonderful to see this long history of digital Earths from all these different places. So we do have some questions in the Q&A chat. First question is from Joanne Lee on how is like WMS or TMS, Cloud Map Services, related to cloud optimized, the cloud optimized concept?
I can give that one a go. So WMS is a visualization service. It's putting images of data out, in a tiling kind of slippy map paradigm. And so it is a web paradigm, but it's not really about getting data. So they're sort of different things. So if you want to do visualizations and optimizing data for visualization, then that's kind of one area. And in the other area, which I've been talking about just now, it's really about optimizing data, for streaming data into analysis. And they kind of cross over a little bit. But yeah, I think it sort of gets down into the technical details. You can sort of stream the data directly out of a cog into a browser, getting rid of the need for WMS, but it's still kind of edgy, and it's hard to know whether that'll scale up to millions of TIFFs, for example.
Okay, cool. I think he or she has a follow-up to that as well. This round, was it? In my head, I feel that was not very cloud optimized. I think she was trying to stream lots of geotips as well. So yeah, it is like tricky if you're working with like, I don't know, thousands or hundreds, tens of thousands of geotips. If you can get away with not having like a WMS or TMS on top to stream out of those data sets. There's
always kind of a race between the different technologies. And I think WMS is such a well-established visualization API that I don't know. We kind of do need to keep supporting that, but eventually we'll have more faster, better cloud native ones that'll take over.
Yeah, and in a way, like the cogs, the overviews built into cogs, you can think almost of that as like the WMTS, right? Having pre-rendered overview tiles for different zoom levels.
Yeah, that's right.
They're not like incompatible with each other. Like you could, theoretically set up a WMS service on top of cogs, for example.
Yep, absolutely.
Okay, cool. Do you have other questions? No? If not, can I ask a question?
Yeah, sure.
Yeah. So you have this, you show this history of like, going from like Digital Earth Australia and Africa, which are good. And for the Pacific, there's usually like more water than land. So are there any like challenges with that in terms of like the way you do the analysis ready, like the atmospheric corrections, for example, over like more water areas than like land?
It's a really important question and concept. In brief, the USGS level 2 corrections were always intended to be for land. And there's this CEOS analysis ready data for land sort of concept, which has been around for a long time. And there's also analysis ready data for water. And so it's different. Now there are products called, USGS has a product called water reflectance. So we're talking surface reflectance. So I used that word before. So you've got the level 1 top of atmosphere, and then you're correcting it so that you're producing surface reflectance data, which is hopefully the same color as the actual land. But then there's water reflectance corrections as well. And I don't have a lot of experience working with it. I just know that it exists and it's a concept. It may be something that Fang has some information about. I'm not sure though if she's got experience there either.
Yeah, it is a more suitable product for water studies, definitely.
Yeah. But yeah, so you actually have an analysis ready data product that's optimized for certain situations. Yeah. It's on the roadmap for Digital Earth Pacific is to work with water reflectance data, but that's all I know so far.
Great, cool. Good that we're, I guess, localizing some of the concepts, so we're not just like taking something from another place and not adapting it to the specific, features of another geography. Okay, let's move on to our next speaker, Leo. You want to start sharing your screen?
Yeah. Here I am. Okay. So my presentation is about a data management system that we are building for a project on the Great Barrier Reef of Australia. I'm part of IMOS, the Integrated Marine Observing System, and more specifically of the AODN, the Australian Ocean Data Network, which is the organization that basically manages all the distribution of ocean data collected by a range of different sensors and projects, so that all this data can be available online, mainly for research and for government policy making. So the project I'm working on is specific on the Great Barrier Reef, and this project started for a reason that can be weird. The problem with ocean data is that we don't have enough data because we have too much data. What I mean with this is there are a lot of different organizations, each collecting their own data and each distributing their own data. Now, the AODN, which is my organization is trying to be a central point that distributes lots of data from different sources, but still it cannot currently distribute all the data that's available. And so for these new project that started on the Great Barrier Reef, we are trying to really manually collect everything we can find from all these different organizations and research groups and put it together in a single Great Barrier Reef data management system. So this data management system is part of the Reef 2050 Integrated Monitoring and Reporting Program, or RIMREP for short, which is a long-term problem with big money put into it by the federal government, trying to get better information about the state of the reef, the state of the coast near the Great Barrier Reef, and to use this information to build better policies and make better laws to manage this reef. What we are building is this light blue section in this diagram, which is the data management system. And as I said, we are collecting data from several providers and distributing it either directly with cloud optimized formats on cloud storage, or we have also a couple of APIs. One of the APIs we have is STAC, the Spatial Temporal Asset Catalog, which is what Alex just mentioned. And it's a very nice and easy to use way to collect information about different data sets, collect metadata about each of them. It allows some search. We're using Python library, which is called Stack Browser, to have this nice web-based visualization where you can search for the data you need, see where it is on a map, and get links to where the data actually is, together with the information about what's inside the data. In addition to this, we have an API to actually get the data, and this is PyGeoAPI, another Python library. This is an implementation of the OGC standards, and it at its core is something you can use from you can write a program to query this API, and you will get JSON results with your with whatever you are querying. You can get the results in different formats. You can get the native cloud optimized formats we're using that I'm going to talk about very soon, or you can get simple CSV or NetCDF or whatever you want. PyGeoAPI is nice because it can be easily extended to manage different data formats. We have written a class to manage Parquet data, and improved a bit on a class to manage Zarr data. But it also provides this simple web interface. That's not the main feature we're interested in, but it comes for free with PyGeoAPI, so we also have this nice website. The link is here, but it's not currently available. We're not in production yet, but we should be very soon, if not next week, early next year. So the data formats that we chose to use are two, because we looked at the data that we needed to collect. This data is of very different kinds, very different formats. We've got, but all these kinds and formats of data can be grouped in two main groups. The tabular data is anything that can be organized in rows and columns. And we've got some data sets that provide us data in simple CSV, JSON, sometimes even Excel spreadsheets, or any kind of vector data like shape files, for example. And we convert all of this tabular data to Parquet, and in particular GeoParquet, whenever we have geospatial information. Another kind of data that we have lots of information about the ocean generated by ocean models. These models produce multidimensional gridded data. They can be quite large. The largest data set we have at the moment is a bit more than 1 terabyte in size, but we've got several of those. And for this data set, Zarr is probably the best option. As Wei Ji was mentioning, it's very good for managing multidimensional data that can be complex, can have several variables in the same data set. So why did we choose to use Parquet and Zarr? Well, again, if you are in this talk, you know that they are cloud optimized formats. They are analysis ready, so you can use them easily to do whatever analysis you want on the data. You won't need to download a full data set or to load it only in memory. So the way these formats are stored is designed to be efficiently used on the cloud. You can access only the portion of data you need. And in our particular case, we have these very large data sets that need to be analyzed by several people and organizations and research groups. And it would be quite impractical if we had each of these groups download all of the data with all of the daily updates just to be able to work with it. So cloud optimize is the way to go. And Wei Ji already gave a quick introduction on these formats. I will just say a bit more about each of them. So Parquet is a well-established standard. It's been around for years, was developed by Apache, and it's a columnar storage format. So instead of storing one row of data after the other, we're storing one column of data after the other. Actually, we're then chunking this column. So we are, for example, storing the first 1,000 entries of the first column, then the first 1,000 entries of the second column, and so on. This is good. This gives us several advantages. In particular, sometimes we have data sets with a very large number of columns, but people won't necessarily be interested in all of the columns at any time. Maybe someone only needs to know latitude, longitude, and temperature from a data set that has hundreds of other columns. And since this format is stored column by column, it's easy to select just few of them and to download only the portion of the data containing those columns. The columnar format allows for efficient compression because you will have similar data stored next to each other. Since we're storing all the values from the same column, one after the other, it's easy that there will be repeated values that are easy to compress. And it's easy. It's possible to do to take advantage of parallelization because you can easily spin up processes that read from multiple columns at the same time. So even if you're just trying to extract a small number of rows, you can still parallelize these and gain speed from that. Parquet stores all of its metadata at the end of the file. So you can simply load the final portion of the file and know everything you need to know about how the file is structured and what's inside. And it can be composed by multiple files. You can store a data set as a single Parquet file, but you can also store it as multiple files, and it's totally your choice depending on how you want to manage it. Maybe sometimes if you want to update a data set, it's if you split it smartly, you can just update a small file instead of having to rewrite the whole data set. Since we're dealing with geospatial data, we are using, in most cases, GeoParquet, which is an extension of the Parquet format. And what this extension does is basically add one more column, which is a geometry column. It stores data in well-known binary, which means it can store any kind of vector information. It can be points, it can be areas, it can be collections of points, lines, and polygons. For the Parquet format, this data is stored simply as binary. So Parquet sees this as a binary column. GeoParquet knows how to interpret this column and can show it, as in this image, as what this binary data represents. GeoParquet also has been around for a while, but less than Parquet. So I found working with it that support is still more limited than the Parquet format in general. But the good news is that for most cases, you can make use of any of the large number of libraries that have been written to work with Parquet. And then when you're specifically interested in geometry, in the geometry column, you can make use of GeoParquet as, in some cases, as a post-processing step. The other format we're using is Zarr. Zarr, the main feature of Zarr, I would say, is the chunking. So we've got these multi-dimensional arrays. They can have 2, 3, 4 or more dimensions. What Zarr does, it slices these arrays into squares or cubes, depending on how many dimensions they have, and each of these pieces is stored in a separate file. Then it has basically an index in the metadata that tells you where to find the data you're looking for, which files contains, for example, if your data set is organized by latitude, longitude, and time, you will know that latitudes between 42 and 43, with longitude between 20 and 21, and time between 2003 and 2004 is stored in this particular file. So with any query you do on these coordinates, you can just look at the metadata and know straight away which files you need to download. And those files will contain the information that you queried for. This metadata is stored in JSON format, in a file that's stored in the same folder as all the other chunks, and you can simply open it and look at it. There's an example here on the right. Zarr was originally designed specifically for Python with XArray in mind. So XArray has very good support for Zarr, but now recently the Zarr version 3 has been designed and it is being released that is a bit more open in its design, so it can more easily be read and managed by other libraries and other programming languages. So another tool that we're using that I didn't know before starting this project, and I've grown to kind of like it, is Argo workflows. So we are managing all of our processing on the cloud. We are using Kubernetes to spin up the pods with containers to do all the separate steps of processing. And to orchestrate all these, we use Argo workflows. This is a framework that is designed for Kubernetes, and it allows us to write YAML file with that define workflows. These workflows can be organized as graphs, direct acyclic graphs. You see a a small picture on here of our workflow run. So you have, starting from the top, each step runs, and then multiple steps can follow each of these steps. Some of them can have conditions, so in some cases you just skip them. Others are run, and then the result of a step can be used by following steps. And each of these steps is actually spawning a pod on the cloud that starts a container and does whatever processing we told it to do. Argo workflows is pretty nice. Sometimes it can be a bit annoying. The error messages could be improved, but overall I've been liking it, and it's got a very nice mascot with this little logo, which is a good plus. Finally, we started doing all these, and then we realized we still had a problem to solve. We need to provide people with metadata about each of the data sets we ingest and we distribute. But Zarr has very good support for metadata. You can define attributes about the whole file. You can define attributes about certain variables in the file, about the coordinates, and give information about each of them. Parquet is not as good. So in theory, Parquet does have support for metadata. You can store global information about the file. You can store information about each column. But in practice, we found out that different libraries store this information in different ways. And so if you try to, for example, create a Parquet dataset with Python and, let's say, PyArrow, it's very likely that you won't be able to read the metadata from this file within, let's say, R and the R version of Arrow. This was kind of a problem because that reduces interoperability drastically. It means that people won't be able to get all the information from our data unless they use the exact same library we are using. So we looked for different solutions, and we found this other framework, which is quite nice and simple, frictionless data. And what frictionless data does is define the concept of a data package. A data package is basically defined by a JSON file like this one. The JSON file can be stored together with the data. The data can be in any format, it doesn't matter. In this JSON file, we have some specific key values pairs that we can provide. For example, name of this dataset, title, description, some links, contributors, and other things. In particular, there will be one entry in this file, which is called resources, which gives you, which basically points to the data. Usually the data will be in the same folder as this data package file, but it can be anywhere. You can give it a URL if you're describing a data set that's available online. And the nice thing about frictionless is that since it's JSON, you can, even if you don't have any library that's designed to work with frictionless, you can simply open this file, look at it, and you've got all the information available. You can read it. But then there are libraries provided for several programming languages that are designed to work with this, so give you some tools to process these metadata file. And the other nice thing is that it's the standard is written to be very flexible. So there are a few predefined key value pairs, like as I said, this one, name, title, description. But frictionless allows you to add any other attribute that you might need to provide with your data. So for example, it's not designed for geospatial data, but we needed to provide some spatial temporal information. And so you see, sorry, at the bottom of this image, we have, for example, an entry for start and end date time, another entry for the spatial bounding box that we've added as metadata to this data package. In particular, since we started all these with the problem for Parquet, Frictionless has very good support to describe tabular data. So there is a concept called table schema. It can be stored in the same file as the data package or in a separate file. And this table schema basically allows us to use again a JSON file to give information about each column of a tabular data set. We can give the name, title, type, format, example values for a column. Something very nice that we can do is give constraints for each column. We can say if it needs to be a value, if these values need to be unique, if there's a minimum, maximum, and so on. And then frictionless libraries will be able to automatically validate the data for us using these constraints. This is quite nice because it's what we wish we would be able to do with Parquet metadata directly, but we're not. But Frictionless lets us do it. At the moment, there is not an equivalent for raster data. We're thinking of designing a frictionless extension to do that, but for the moment, we're happy using just the built-in support in Zarr for metadata. So this is basically all of it. Just wanted to show you the people behind all this. We're a small team. We started working on this basically less than a year ago. And yeah, we are happy about the project. We're about to publish it and go to production. We're all very excited about working with geospatial in cloud native. Thank you. And if you have any questions, I'm here.
Awesome. Thanks, Leo, for diving into some of the internals of like the Parquet and Zarr specs, and also giving us a good lesson on what it means to write good metadata. Because I think you can have as much data as you want, but metadata is also very important to to describe what's inside. And so thanks for sharing that. We do have one question for you in the chat. Seems to be specific to IMOS. So Joanne Lee asks, is there a timeline for IMOS to convert all of the GBR data roughly? And also, what would be the biggest obstacle during the whole process in your opinion?
Okay, so all the GBR data is a very big ask because the hardest part is actually finding what data is available. And there are new projects and new data sets constantly being published. What we are trying to do for the moment is we have a list of data sets that are of interest for the Great Barrier Reef Foundation. This is a government agency basically managing the Great Barrier Reef, monitoring its status and trying to protect it as best as possible. So this foundation did an analysis of all the data sets available and found there's roughly 350 different data sets that they are interested in to be able to get all different kinds of data about the whole region. So in this stage of the project, that's going to end in June next year, we are aiming to collect and ingest at least all those 350 data sets. So what I can tell you is, yeah, by June next year, we will have all the GBR data that the Great Barrier Reef Foundation thought is interesting. Then we don't know for sure yet because we don't have a contract, but if this project gets renewed, it will keep going and it will keep adding more and more data sets to the list. But this will be an ongoing project because we won't ever be able to say, okay, we're done. We've collected all the data about the Great Barrier Reef, because there will always be more studies and more data. And oh yeah, the second part of the question was about the biggest obstacle. And I would say there's a couple of obstacles. One is having access to the data. In some cases, organizations may put barriers in front of their data, which is not very nice in general, and it's a problem for us in particular because yeah, we're trying to collect hundreds of data sets, and for lots of them we need to contact the organization collecting the data and make some kind of agreement for how we can access this data and how we're authorized to use it. And the other problem is some of these data sets are not very well organized. So there are some of them that are in weird formats, or they have errors that make processing the data hard because we keep getting exceptions when we try to convert it or try to find the right types to store each column of data or so on. And so some of them are well done and it's pretty straightforward to write a pipeline for them. Others, it takes a bit of trial and error and a lot of work to do.
Okay. Yeah, glad to see that the problem of reading data hasn't really gone away yet. But that's the point, right? With cloud optimized data, we're trying to make it easier for the user to not have to go through all of that.
Yeah,
and that relies on like standards and interoperable standards. So we're thanks, Leo, for you and your team's work on this. I'm sure a lot of people out there will really appreciate it.
Thank you.
Okay, cool. Next, we'll move on to our final speaker for today, Fang Yuan from FrontierSI. Cool. Do you want to start sharing your screen?
Yep, I do. Intention. Oh, you able to see my screen all right?
Yep, we can see it.
Thank you. Thanks, Wei Ji. Yeah, thanks for inviting me to this webinar. I've already been learning a lot of things. I guess my perspective might be slightly different, more from application developers and probably a bit on the end user as well. So my name is Fang Yuan. I'm currently the Earth Observation Technical Lead at FrontierSI. I have been involved in Digital Earth Australia and Digital Earth Africa for quite a few years as well. So my role is mainly focused on application development, but I've worked very closely with developers, and I would say that nowadays, we deal with so large amount of data and trying to develop an application that can be scalable. And so it's actually quite important for the data scientists to be at least understanding the basics of the data formats and the implications as well to make that process a lot more efficient. So a lot of the work that I'll be presenting today would also be done by my team members. So I lead the insights team inside FrontierSI, and we also have a data solutions team. So I'll be presenting mainly a project that we've done in the last few years and I will continue to develop as a use case, but I think I'll also try to talk about why I think that cloud native geospatial is important for us. So I can move slides. For those of you not familiar about FrontierSI, we are a not-for-profit organisation based in Australia and New Zealand, but we do work with global collaborators to develop solutions. So what we see our role as bringing together organizations across government, universities and industry to try to solve big problems. We have expertise in space advisory, geospatial technologies, earth observation, data analytics, and also positioning, navigation and timing and geodesy. So as I said, we work closely often with our partners to solve problems. And I'll just give you a list of, I guess, recent projects that's done by our technical team internally. This is certainly not comprehensive, but hopefully give you a sense of the wide range of things that we really do within Frontier. We've been working with the Open Data Cube community for quite a long time now, supporting Digital Earth Australia and Africa in various science and technology development, in industry engagement. And we work using these various platforms to develop applications or try to help them improve their data products for end users. And we also, for example, working with Cyro's Easy platform, a similar Open Data Cube-based platform, to run hackathons and user trainings, and try to help with a lot of the user engagement. And we also work kind of a slightly different, few other slightly different projects. For example, we developed a tree ledger and tree density mapping for the entire state of Victoria for Victoria government. And as part of that, then developing a method for them to continue to produce that data set from time to time using high resolution aerial imagery. And we're also involved in standard development as well. Just as an example, the machine learning training data set engineering report for OGC. And there are also a few other data management projects that we support. And within the space of Earth observation, our expertise kind of lie in coastal mapping, land cover, agriculture field mapping, water, and vegetation. And why cloud native geospatial, and I guess the other discoverability and interoperability that other presenters has mentioned, that's important for us. As I said, a lot of the times we are consumers of EO data ourselves because we try to derive insights from the EO data. And we want to be able to access the wealth of data products. It's already out there. There's so many accessible through the cloud. And we want to be ideally developing workflows that can be easily adapted to work with various different data sets. So even though we're not entirely there, there's certainly lots of progress in that direction. And often we're developing solutions for our end users or clients that's not EO experts or technology experts themselves. And so we want to help them develop solutions that will likely be sustainable across the times, and they don't necessarily have to maintain those expertise themselves to be able to use the solutions we provided. And so therefore, I guess I picked this project as one of the examples that as our use of cloud native geospatial. It's probably slightly different to the other presenters, the presentations, but this kind of gives a different perspective, I think, for some groups of users. We need to be flexible in terms of how we develop solutions that will help them. So the ENVestigator project is actually, we've been developing this for quite a few years now. So in the last 3 years, in particular in collaboration with the Curtin University, and also importantly, working very closely with mining companies and regulators, we developed this toolkit to help map groundwater-dependent vegetation. So while the GDV is started as the main focus of the project, we ended up developing a tool that can map various vegetation covers and do vegetation monitoring, species distribution modeling. And we actually, because of the usefulness of the tool, we decided that we are going to continue to expand the toolkit and add more functionality to it. And we've designed it to be an ArcGIS Pro plugin based on what the user community or the target users of this tool is. So a little bit of background or context of why the groundwater dependent vegetation is important. So it is one type of sensitive ecosystem that is often impacted by mining practices like water extraction. So the mining companies, therefore, are actually responsible for identifying potential groundwater-dependent vegetation systems and provide monitoring, reporting, so that to minimize the impact through their mining practice. So how it's done in the past, usually done by ground surveys. And as you can imagine, this is both very expensive and also not very complete, because you can only do this every few months or year. And you go out and basically, this is the kind of the landscape that's typical in West Australia. Like you basically try to pick the vegetation that you think are potentially groundwater dependent vegetation and collect samples. So you're sometimes missing the actual GDV communities, and also missing the times when it's the ecosystem actually has degraded. So the tool that we've developed is really targeted to help this kind of situation. So we want to be able to use the satellite imagery to provide that near real time or quick information as a new acquisitions or the imagery is acquired to provide recent analysis of what is happening to the vegetation cover on the ground, and then provide that early warning to the ground team, so that even if additional ground surveys is required, they can be very targeted and so cost effective to provide the most useful information, and actually be efficient in mitigating the impact as well. And also because we've developed the tool to work with public data sets, so it's actually can be adapted to use pretty much anywhere in the world. And just, I guess, a quick overview of the actual tool itself, just going through the components of what it does. It's ended up being a suite of toolkits that people can use either in combination to analyze ground cover, or just separately to help doing all type of analysis as well. So as I said, this is a ArcGIS Pro plugin. So the first step, does start with just accessing and retrieving the satellite data. So the current setup is to get analysis ready data from the Ditial Earth Australia platform from AWS S3 bucket and through the stat catalog. And the next component of the tool is about the actual groundwater dependent wet vegetation modeling. So we're actually looking at implementing a couple of different methods to map the GDV. So one, looking at the spectrotemporal distribution and comparing the all types of vegetations to pick up the signatures of the GDV. One is looking at their phenology patterns across time to try to use these metrics to separate the GDV from the other type of vegetations. And then also looking at species distribution. So, this is on the spectral information. So still looking at how do we use known information about vegetation covers from high resolution imagery to kind of extrapolate that to map larger areas of vegetation. And also looking at additional variables like such as the topographic variables that informs the species distribution of the different vegetation covers. So and we can then combine the different pieces of evidence generated by these different methods in an ensemble tool to really give us the more holistic picture and understanding of where GDV or sensitive ecosystem might exist, and also do a bit of an uncertainty analysis if the evidence either match each other or actually conflicting. And there's a slightly different separate piece of tool that's also developed, is actually doing near real-time monitoring using, again, the public available data sets. Is actually for an area of interest, you can actually retrieve the baseline time history of observations. And so the model is built up understanding of the trends of the vegetation change. And it will also help you grab additional data when that becomes available. And so when a change is detected, it can send you alerts, and so that you can actually be prepared or investigate what is happening. So I'll just I will not go through all these different parts of the tool in detail. I've just to pick two. So one is the kind of the core module of doing the groundwater-dependent vegetation itself. So we're looking at combining the time series data that we retrieved from the Cloud Optimizer GeoTIFF tool itself, and looking at the seasonally weighted signature. So the groundwater dependent vegetation, because they're fed by groundwater, so they tend to stay green and with a high moisture content over time compared to the other type of vegetation. So we can use that difference to pick up the likelihood of GDV existence. And so this method has been validated in the Pilbara region in West Australia, and to be quite successfully picking up the GDV communities. And so the example on the right-hand side really just gives you a sense of, for this particular area, the tool is able to identify the different kind of likelihood in the region, and the GDVs tend to be along the drainage lines in that area. And the other one, as I mentioned, I think it's quite interesting, is the near real-time monitoring. So for this one, you do pick an area of interest, and then you will look at, the tool will look at the historical time series. In this example, it's normalized difference vegetation index, but it could be a different type of index or particular features that you want to track, and then use that pattern, the long-term trend, to see where the trend changes to identify any potential deviations. And then just a quick kind of actual example. So for this particular location, the tool will be able to calculate the historical the time series, and then run a change detection algorithm to map where the deviations has likely happened. And then if it is a negative deviation, and you can set the threshold where you get the alert as well, and then you'll be notified when that change happens. And you can configure the tool to continue to run and retrieve new observations when that becomes available. And so just for the technical audience, like just a very quick picture of the actual architecture itself. As you can see, that the front end is configured to as an ArcGIS plugin, but the back end is really running Python modules and using OpenDataCube Xarray to query the stat catalog. Although this hasn't been as well developed, but it is also possible then to run Python modules in the front end to conduct some of the analysis, so you're not really limited to just use the ArcGIS Pro tools. And in terms of the data flow, so the users will be able to pick interactively their area of interest using the ArcGIS Pro interface, and then the tool will query the Stack server of Ditial Earth Australia, grab the data through the OpenDataCube and from the AWS, and then save the data locally. So even though the analysis is actually done locally in this case, but it's actually worked out quite well for people that wanting just to do analysis of their local area, because it's actually quite efficient, and this helps them to not having to deal with a large amount of data, and it's actually quite manageable. And just a couple of last comments. If you're interested to know more about the project itself, to go check out our website, and the previous development of the tool, which is actually called Tenement Tools, is available as an open source code on in our FrontierSI GitHub repository. And as I said, we are continuing to develop the tool and expand its functionalities. And a lot of that is actually driven by the needs identified by the users. So the mining companies and the regulators who are going to use this tool actually themselves. And so it's very important that we understand what's their pain point when they use the tool, whether it's intuitive to them, whether it's solving their needs, and also they trust the models and the methods actually used in those in that tool. And we do user training as well, and it's actually a really good opportunity to find out how people are actually using the tool to understand how we improve it. And I did want to mention that even though I'm not expanding on the other project, we do use cloud-native geospatial things like COG, and we're actually exploring using of GeoParquet for the Africa support project as well. So we do use kind of these technologies all the time for other projects as well. So a lot of the times we do time series analysis, grabbing the open data using the ODC stack tool that Alex mentioned. And also, interestingly, I actually find it quite useful to use the COG and point it to the Tyler. I think it's a development seed project to actually run WMS, because often we have users that's just needing to have visual ability to check the data. And also we've developed the web-based dashboard to kind of help showcase the work done as well. So it's actually a quite easy setup and very efficient for users to get access to those insights and data just for visual. I think that's pretty much the end of my talk. Happy to answer any question or just contact me by email as well after the presentation. Thank you. I'm just gonna stop sharing.
Awesome. Thank you, Fang Yuan. That was a very interesting talk. Learn a lot about how you're integrating it, I guess, like the remote sensing side of things, but also looking like on ground surveys, because and all of like the time series modeling as well. It's super cool work. Does anyone have questions for Fang Yuan? Okay, yep, we've just had 2 questions pop up. One from Negan Mokhadam. So thank you, Fang. This is an amazing tool, especially with the significance of GDV in regional Western Australia areas historically. One question that I have is whether users can query for more than one area of interest when using this plugin.
So for the data retrieval part, you have to do it one at a time. For some of the analysis tools, you can pick kind of multiple small area of interest within the data that you've retrieved to do analysis. Does that answer your question, Megan?
Yeah, we can try to unmute. Yes. Yes, thank you. Cool. We have another question from Luis. Hi, is the ENVestigator tool available? Do we need to buy a license for it?
Yeah, so currently we do have an open source version of it, which is kind of the result of the past 3 years of development. I'll find that link and paste it in chat as well. So we are continuing to develop it. So we don't quite sure about the future yet, but currently you certainly can get access to what's already available.
Okay.
Oh, you do need an ArcGIS license, though. Just want to that part is not covered by our tool.
Yep. Okay. Thank you. Cool. Is there any other questions? If not, I do have one question, I guess. What do you think of like, so you've covered like the remote sensing with the COGS, right? Where there are like optimized formats for that. But what about like the in situ data? Are you aware of any cloud native formats for, I guess, like the time series data that's collected from in situ sensors?
I'm not aware of people, like specifically people doing that, but I certainly think that like a lot of people are starting to share the in situ data, and they're very critical for the application development. So if not already using the cloud native format, I would certainly, if we have opportunity to work directly with those data, we would certainly put them, share them in those format.
Yeah, because those like Internet of the Things was supposedly going to be a big thing, right, a few years ago, and that's where you get lots of like streaming real-time data from sensors. And yeah, I'm wondering if there's like people have worked on that to integrate that with like satellite remote sensing data. Cool that you're thinking about that. And okay, do we have other questions? If not, we can. We have about, I think, 15 minutes left to so we can open up to the entire panel for any questions. So if the way this works is you can either raise your hand to ask a question or just put it in chat, and the panel will answer them or discuss them. Should we start? Does anyone have any burning questions? Do you want to start from the panel? Discussion points? Nope, everyone's shy. Let's see. Any questions? No. Okay. I can start with a question maybe. So I think one of the questions we had just now was around like tabular formats like GeoParquet and raster formats such as Zarr. Are there ways to like make it easier to interoperate, like convert between, like integrate those two formats? Are they like existing standards, such as because like with GeoParquet, for example, there's like the arrow standard, which allows for efficient transfer of data. But is there something out there now for like raster data that's similar
I'd say
to
it's
arrow?
Xarray is kind of like the in-memory data format standard, and it's kind of like a lazy loaded model for it all. But it's really closely related to Zarr as well. Like my layman's understanding is Zarr is really like a way of rendering an X-ray into a data storage format that works at a big scale. And that then raises the issue that it's kind of Python only. And so like we've kind of left the R data science people behind a bit by having Zarr and Xarray working so well. And like the Open Data Cube and related tools are really they're sort of structured around getting TIFFs or GDAL ready data sets and loading them into a time series Xarray as well. So it's like most of the job of the Data Cube is in doing that, and then working with the Xarray in memory. So again, it's like a Python space. So in terms of that data science, I think there's like it's important to remember that there's other ways of working other than Python, and to make sure that we consider interoperability there. And I think that's something that Leo has been part of your project, is making sure that you at least support R and Python, right?
Yes, and it's not been easy. And we actually don't have a perfect solution for this. So yeah, at the moment, Zarr is basically designed for Python. As I said, there's a new Zarr specification, Zarr v3, that's supposed to be easier to implement in other languages, but I'm not aware of any libraries, for example, for R that are that work well with Zarr at the moment. So currently we have our data API based on PyG API, and people working with R, we suggest them to use that. So instead of trying to access the cloud optimized data on the cloud directly, they pass through our API. It's not ideal, but at the current situation, that's the best we can do. Hopefully there will be some development to make this more available outside of Python.
There's another R library that will kind of wrap around Python data structures and make them available in R from memory. I forget what that's called.
Yeah, I don't remember the name either.
Is that
but
Reticulate?
Yeah, it's Reticulate, yes.
Yeah.
But that makes it a little bit harder to write code, and yeah, it's not the same as having native support.
Yeah. But from the way that I've been working lately, having X-arrays, kind of the in-memory interoperability layer for Python is hyper productive.
Oh yeah, it works very well as long as you're using Python.
Yeah. So someone needs to port X-ray to R or Julia or one of those other languages, and we'll all be happy. Okay. And another question I had was, or like the question the audience kind of had was around WMS or TMS versus like cogs. I know Fang Yuan, you mentioned that you were using cogs with Ditial, which is like a dynamic way of like serving cogs to web users. I guess my question is, would that sort of like dynamic tiling method be the way to go forward, or would that still be like a place for traditional like WMS or WMTS services? Like, what are like the pros and cons of those two ways?
Must be on the kind of the backend technology side, but I would say for us, sometimes that's because people already have working with QGIS, for example, so that's easy to just spin up the WMS and then people can directly use. Although I realized that you actually need slightly different WMS for QGIS and ArcGIS Pro, so which means it's not really a one fit all solution either.
Yeah. And when it comes to Earth observation data, you've got this like long time series. So you got the temporal aspect, and then Landsat and Sentinel-2 are sparse spatially. Like they've got a strip in a day, and then the other strip's way over there, and so you've got big gaps. And it's quite awkward when you try and get that working with the desktop GIS paradigm. You know, you kind of want to just switch to having an annual summary or a single scene, and you miss out on a whole bunch of the opportunities of the whole cloud native vast data access kind of space. But I'm not sure if there's any way to neatly bridge the gap between, you know, desktop GIS, which kind of doesn't have a temporal aspect, and data science where you're working with big lazy loaded arrays of multi-dimensional data.
Yeah, because I guess with like traditional WMS, they like normalize the colors, for, if I'm not mistaken, to like an 8-bit format as well.
Yeah, or
whereas,
it's a
like
PNG or a JPEG. Yeah.
Yeah, whereas like sometimes if you're doing like proper analysis on it, like to calculate NDVI, for example, you actually want the raw pixel values to run those band index computations. So
yeah, that's right.
That's probably one of the benefits of like dynamic tiling versus WMS, which
so there's always
which is more like visualization.
There's always the two standards, the WMS for visualization and WCS or coverage service for data. But I've never seen a compelling use case for the web coverage service, because it doesn't really work as a bulk data access API, and it's almost trivial if you try and use it for a small data set. And it's one of those abstraction APIs that's it's got a really narrow niche, I think. I don't know if any of the other panelists have experience getting good value out of WCS, but I've never found it useful.
Yeah, my personal feeling is probably it's a different audience users, because certainly like my team of data scientists are happy to just use Python or other methods to work with the data. And for WMS, we're usually, really serving end users. And it's a really powerful, I have to say that it's really powerful for people to be able to see the imagery, like help them kind of make the data a lot more intuitive.
But there's the visualization of the data and there's the accessing the data, and they're kind of two different things.
Definitely, yeah. So I think that's really powerful for kind of the end users who you're trying to kind of convince them the value of the data and help them understand the data. I think Leo, I cut you off, did I?
Oh, Leo, did you want to say something?
No. I don't have experience with WMS or WCS, sorry.
You're already in the new world of cloud optimized cloud native formats.
Well, you've got a OGC API for coverages implementation, don't you, Leo?
Yes, we do.
Have you
but
used that in anger?
I've used that as it comes out of the box. We use PyGPI for that, and I'm not experienced in like at first I was like, what does this coverage word mean? And now I know a little bit more than that, but not much more than that.
What else? We have 3 more minutes left. Let's think maybe about like the cloud aspect of this. Like, maybe to the panelists, like, are you doing most of your processing now in the cloud, as in like it could be AWS or like a HPC environment, or do you still like, what's kind of like your workflow compared to, I don't know, like 5 or 10 years ago when this technology was a bit less prevalent?
I for the Earth observation data, I source all my data off the cloud, but I'll run small areas on my MacBook, and it's only when I need more memory that I lift the computation up to the cloud, and then when it becomes really big and broad area, that's starting to use Kubernetes and Argo workflows and other tools to really scale stuff up.
For us, it's basically all on the cloud. I run some computation on my computer only while developing. Maybe I need to test some code on a small portion of a data set just to make sure what I'm writing works before spinning it up on the cloud. But then all the main computation is done directly on the cloud. And that's very different from how it would have been done a few years ago. But it's quite nice to be able to do that. And since the data is stored on the cloud, if you're able to run, as Wei Ji was saying in the beginning, if you're able to get your computing close to the data, that makes everything way more efficient. Like from the simple tests I do when I try to do any kind of computation on my machine, doesn't matter how good the internet connection I have, it's much slower than when you can do it on the cluster. In our case, it's AWS. The cluster is next to S3, has fast access to the data, and everything is way more efficient.
Yeah, for our organization, it's definitely a combination, I think. But for large scale processing, definitely just in the cloud. And personally, I use quite a bit just for the flexibility as well, because for a long time I used a Windows computer. I just can't really work efficiently. So yeah, definitely cloud gives you the most flexibility and power to kind of scale up and down.
We're all a bit biased here, being as part of the cloud
I think,
native.
There's a bit of a bias, but I know, Alex, I guess for like the Digital Earth Pacific platform, where the target audience for some of that is like the Pacific Islands, where maybe, I don't know, like the infrastructure isn't as well set up compared to what we have in like Australia and New Zealand. So how's the that transition been going?
Yeah, it's look, I haven't been out into the islands running workshops and working with the people yet, so I haven't got a great answer there. But we worked on Digital Earth Africa for a few years, and I have an image that shows that like there's vast regions of Africa that don't have access to the internet. And so we have 2 or 3 petabytes of data that's available for people to stream, to do whatever they want with. But if they don't have access to any network at all, then it's kind of ridiculous. But there was a researcher called Timon, and I can't remember his surname. And he was working out of Europe, working with people in Mozambique, doing, I think, soybean cropping. And he would assimilate those petabytes of data, run analysis over some of the data over the last week over these people's fields, and then break that down into an SMS and send them like 140 characters, a summary of what's happening in their fields. And I think that's a really cool example of how you can get this big data and this fancy cloud compute and all of this kind of modern technology, but make it really useful for people that just have a mobile phone.
That's the dream, right? Just run everything on our phones. Okay, I think we have one. I think we are past our time, but there's like one more question from the Q&A chat, which I guess we can finish off with. It kind of relates to the previous question. So, like, what platforms do you use when computing on the cloud? Not like the storage part, but the processing tools such as like GDAL or ArcGIS tools. Does anyone want to answer that?
All of them, I guess. So we use the various Digital Earth platforms, Jupyter Lab environment quite a bit, and certainly I set up my own Jupyter Lab sometimes to do analysis. But interestingly, we did have a recent project. We ended up spinning up Windows machines in AWS to run ArcGIS Pro as well, because we were trying to do a bit larger area analysis, and it's just not possible to just simply scale up our local laptop. And so that actually ended up being a really good flexible solution.
Oh, interesting. Is ArcGIS Pro still limited to Windows and Mac? Like,
not
it
Mac.
is
I haven't used
only
ArcGIS for
Windows.
just
Only
Windows. Okay.
Yeah.
Okay. So like it doesn't run on Linux or Mac OS yet. Oh, yeah. Interesting. Okay. Okay, I think we probably should finish off this. How should we finish this? So I guess, yeah, like thank you everyone, to the panelists and to everyone who's attended this. We'll put the recording up on YouTube after a bit of editing. And yeah, and do check out the Cloud Native Geospatial Foundation's blog for the upcoming webinar for Africa, if you're interested in that, or also new users. And there's also like, for those of you on the eastern side of the Pacific, there will be a GeoParquet sort of workshop, I think, next year. There was a blog post on this that just got put out. So if you're interested in that, do check it out. Okay, cool. Thanks, everyone.
Thank you, Wei Ji.
Thanks, Wei Ji.
Yeah, thank you, Wei Ji. Thanks all.
Stop recording.